going to talk about take control of your CAPEX and OPEX budgets using quick connect digital substation designs.
Yep. Thanks, Andy. And thanks for having us to talk about this topic today. And thanks everybody for your attention. Yeah, as Andy mentioned, our topic today is taking control of your CAPEX and OPEX budgets. And I also have Chris Dyer on the line as well, a colleague of mine at Power Engineers, and introduce ourselves a little bit more in a second. The agenda. So first, we're going to talk about a couple of some issues that we see commonly with both conventional substation design and bottom-up digital substation design. And then we'll get into the main topic of today of a few things that we can do to overcome some of those issues. First, a little bit more detailed introduction. Andy mentioned we're a part of Power Engineers, and as of late last year, we are now a member of WSP, an international company that is a global has a global reach for engineering consulting services. Myself, I'm out of the US. I mentioned Chris, also out of the US, and then Sina Karimi is also another digital substation SME out of Canada. And all three of us participate in Working Group 10, as Andy said. We have participated in the IOP for the last 4 years, I believe. Our main role there has been to develop the system configuration files for all of the testing, and last year we used 4 different system configuration tools, and Helinks STS was one of them. We're also active in various C-grade working groups, and we've been involved in digital substations since around 2010 when we first created our IEC 61850 lab. And so let's get into some of the challenges that we're seeing utilities are facing with conventional substations. Of course, we have all of the issues that come along with wired signals, the amount of time it takes to install them, test them, make determinations. You don't have great visibility in a lot of cases of any potential failures with the wiring. And the drawing standards, utilities do a great job of developing drawing standards and templates, but a lot of it still comes down to copy and paste today. So there's although there's starting to be, there's still not a lot of intelligence behind, especially the PNC drawings. And so I've highlighted, or I've bolded a few of these topics here that this presentation is going to touch on specifically. When we move into digital substations, we run into issues of how do we bridge the engineering documentation from conventional substations to digital. So what I mean here is we have in a conventional substation, we're going to have the full set of drawings from the single lines, 3 lines, schematics, wiring diagrams that document the whole substation. When we move into the digital world, some of that stuff moves into the configuration files and communications. And so, there's a question, especially to utilities who are new to digital substations, how do we bridge that gap for different stakeholders, from engineers to testers, maintenance and operations technicians? We also, a typical way to start a digital substation is from the bottom up, which means that you have multiple tools to deal with, depending on the number of vendors that you're integrating into your substation. Some other topics, these two we're not going to talk about in a lot of detail today: substation testing with test mode, version management heard mentioned in previous projects. And then the last one here is trying to minimize the amount of work on site. And again, we heard a little bit about this earlier, and so we'll get into some more details there. So what opportunities do we have in front of us? We seen some opportunities to reduce our CAPEX and OPEX budgets, so capital expenditures and operating expenditures. For those two topics, we can do things like reduce the number of panels that need to go into a building. And when you reduce the number of panels, you can have the opportunity to reduce the building size itself. And those buildings are not cheap. Taking space away from there is a good way to save significant amounts of money. And then the one that everybody thinks about is reducing copper costs, including pulling, terminating, and testing. Some of those costs can drop significantly. We also see a opportunity to reduce schedule by shifting around when some of the testing occurs throughout the life cycle of a project. And uh, the schedule is important. I'm assuming it's similar to where you all are located. In the U.S. here, we're seeing a large demand for new substations due to a couple of drivers. The first one is renewable interconnections. Solar is the big one right now, but also wind interconnections are driving a lot of new substation development. And then we also have new load connections. Data centers are a big one here for us that are really driving the need for more substations, more switching stations, on top of just general electrification, like EVs, large EV trucks for shipping are all driving the need for new substations. Just a couple of definitions here. These taken out of Alex's book I've got right here, Digitizing the Electric Power Grid. We're going to be focusing today on digital substation, and the definition from Alex's book is substations where all interfaces between the sensors, IEDs, and other devices performing pack measurements, monitoring, and recording are based on digital communications, predominantly using IEC 61850, and the only hardwired interfaces are the power supply and the interface to the primary equipment. So, for example, circuit breakers and switches and power and instrument transformers. So that's our main focus today. One other one that I'll point out, we might come across some of these acronyms later on in the presentation. Standalone merging unit, or SAMU, or just merging unit, MU, switchgear control unit. So the standalone merging unit, when we use that term, we're talking about just the analog to digital conversion part, the PTs and CTs, for example. The switchgear control unit, or SCU, would be the binary interface to, say, a circuit breaker where you've got trip and close signals and breaker status maybe. And then if we use process interface unit, we're talking about a device that combines those two pieces of functionality. Okay, when we say quick connect digital substations, and this isn't necessarily a new topic or a new idea. It's not something that we created, but it is something that we're seeing more of. And what we mean when we say this is the building, the control building with your protective relays, meters, network, most of the network equipment can be assembled in the factory, including all the wiring of the wiring and installation of the panels can all be done at the factory. And then potentially at a different facility, different factory, maybe from a completely different vendor, we have the PIU cabinets that can be assembled and wired. And when we uh, when we do the control building uh, construction, we can almost fully test that control building because of the digital nature of the protective relay and meters and IO modules and so on that we're using, the IEDs. And using the test equipment at the factory, we test the protection schemes by injecting from the test equipment, just as if the the merging units were there. We can also send trip and close commands from the relays out, to the test equipment, which again is mimicking the switchgear control unit out at the breakers. And so by doing this, we can know that at the time that that building is shipped to site, we've already tested all of the signals, goose sampled values, MMS that are going to be coming into or leaving that building. While this testing is happening at the factory, construction can be occurring in the field. And so the foundation for the building can be there. You can run the fiber optic cables and the little bit of copper that you're going to need for power and control. And all of that can be there waiting for the building to come. And so when the building arrives, you drop it in place, run the last little bit of fiber and copper and do the terminations. Similarly for the PIU cabinets, you can have digital test equipment, analog test equipment that can inject into the PIUs, and then also the test equipment can subscribe to those sampled values and ensure that you are receiving the information that you expect. You can issue trip and close, for example, from the merging unit or the switchgear control unit to the test equipment, and again confirm that the programming is done correctly, the wiring is done correctly inside of that cabinet. And similar to the building, while this is happening, the foundations are being set, the cables are being run, and then you drop these cabinets in place. And then so now once you've gotten to that point, you have tested your control building, you've tested each of the PIU cabinets, and the last piece of testing that really needs to happen is you need to test this from an end-to-end configuration to make sure uh, that the relays are actually getting the correct sampled values from the merging unit, that the relays are publishing the correct signals to the merging units, and the PIUs are doing what they're supposed to do in terms of tripping and closing and publishing breaker status. And so again, you can do this with some test equipment out at the field and move up down the line. And the important thing here is that because you've already tested the each building and each cabinet individually, the amount of testing that needs to occur in the field can drop significantly. And I think it was mentioned earlier, the importance of that is once you get to site, the level of stress, the number of people that are looking over your shoulder, uh, there's a schedule bearing down on you. And so minimizing the amount of time you're on site doing testing is a big advantage. All right, now we're going to move on to the topic of the engineering process. And in a bottom-up design, I've got an example here showing 4 ICTs, meaning that we have up to 4 vendors included in our project. And typically what has to happen if you do the bottom-up design is ICT1 is going to have to send its current configuration over to ICT2 so that ICT2 can do all of its subscriptions from ICT1. And then 2 is going to have to send its configuration to 1 so 1 can subscribe to 2. And you can see the lines that are being drawn in the graphic. You have a large number of combinations and a large number of file transfers here. And this number grows exponentially as you add a number of as you add new vendors or new software tools. I think 5, if I remember the calculation, comes out to 20 file transfers. I was actually talking to a utility who uses like 7 or 8 different vendor products in their substation designs. And so I didn't even do the calculation there, but you can see the number of file transfers it takes to get everybody sharing all the same information. And something like this might be possible the first time you go through it, right? But I know in my experience, I almost never do this just one time, right? There always something changes. I realize that I maybe messed something up during the QA/QC process, and you have to go back and do all of these file transfers potentially multiple times. So you can see how challenging this is, how time consuming it could be, and how error prone it might be. And when we talk about the IEC 61850-6 engineering process, it introduces the idea of a system configuration tool, which is why we're all here today. And in this case, each of the ICTs publish the ICD file to the system configuration tool. And all of the engineering is done inside the system configuration tool for the whole system, no matter how. Sorry, I just saw a message that you lost me. Can you all hear me okay
Yeah,
still?
we can hear you again. You just cut out for a second, but now it's good.
Okay. Okay, thanks. And so the system configuration tool does all of the Goose sample values MMS configuration. As we all know here, the Helinks STS is the system configuration tool, and then the system configuration tool publishes one file back out, the SCD file. And yes, that has to go back to each of the four tools in this case, but it is one file that contains the entire configuration. And we'll see a couple of we'll see at least one idea next on where that's beneficial. So I'm probably preaching to the choir here a little bit, but the system configuration tool introduction in part 6 is a huge time saver, makes us more efficient, less error prone, and really addresses the issues that we saw on the previous slide in animations. As I was saying, the SCD file is the one source of truth for your substation configuration, and there are a number of benefits that can be derived from having that SCD file. A number of vendors today are able to do things with automated testing tools based on the SCD file. Some of them can automatically draw diagrams in their testing tools. Um, there's network configuration tools that can do a lot of the network engineering based on the SCD file. What I'm showing here is what we call a signal flow diagram, and this is generated by a tool that we've written that reads the information in the SCD file and generates these signal flow diagrams. And if you remember back at the beginning of the presentation, I mentioned one of the issues that we commonly hear from utilities is bridging that documentation gap from a conventional substation to a digital substation. And again, we're not the only ones to create these diagrams, but one of the unique things here is, again, it's created directly from the SCD file. So the tool generates one of these diagrams for every IED in the system, and potentially two, because it does a separate diagram for the Goose and a separate diagram for the sample values. And the one IED in the middle, the big one there, that's the focus of this particular drawing. And on the left-hand side of that IED over here is the inputs that you have in the configuration, and then on the right-hand side are the signals going out and the Goose control blocks that are being published in. And then all the way on the right-hand side are the receivers of those signals with arrows connecting to their inputs, a shortened form of the input. And then on the left-hand side are any IEDs that are publishing to the main IED in the middle. And we have some simplified information here um, with the control block name and then the signals included in that control block that are being published to this IED. And the main idea that I want to get across here is that how powerful that SCD file is. By having all of that configuration in one file, you can do really interesting and powerful things with creating documentation. This is just one form. It's also possible to create, a written Word document that extracts information out of the SCD file. And I think we're just now starting to see some of the creativity and innovation that's going to come along with having those SCD files, that single source of truth. And the next part of the presentation I want to talk about a little bit is continuing to build on the SCD idea and making use of templating. And you're going to see some screenshots that do come from Helinks in here. We're going to be talking about Bay templates and then Goose and sample values scheme templates. Okay, and let's see. So this is an example of a Bay template. We're going to see a more full substation made out of this template, but this is uh, this is a template that's used in a ring bus architecture for a project that we did. You can see we've got the transmission line, two CCVTs. We've got the bushing CTs on the circuit breaker one. If we dig into uh, the Bay template, we can see the function allocation. This is a simplified version of it, but we have um, our circuit breaker XCBR. We have our TCTR, and of course in here, as you all probably know, this is where you define the signals that are going to be published by these logical nodes. We do have our HMI in here, which is going to be an MMS receiver. And then we have a couple of functions in here for receiving the goose and sampled values, functions and logical nodes. And so this is where the system specification comes in. You can tell by the chain that's broken here, we're not actually implementing these IEDs yet. This is all on the specification level. Once we have the Bay template configured, we see we can go in and configure our Goose and SV schemes. You all are probably familiar with these screens from STS. And on the left-hand side are the publishing devices. Across the top are the subscribing devices. And then the checkbox indicates that that subscriber is listening for data from that publisher. One thing that we did on this project is we made use of the automation uh, equations in the STS tool in order to allow us to automate the connections of these publishers and subscribers. And I've got a video here coming up that will talk about that. So here's a short video that I'm going to show. This is that four breaker ring architecture that I was talking about earlier. I've got 3 of the 4 bays configured, and what we'll see is the use of the bay template to automate connecting the sampled value signals here. So just showing here that we've got the first 3 bays are allocated to our roles, and then come back to the single line diagram, click the bay out of the library, drop it on the single line, and we do have to do a little bit of configuration here to tell it where it lives in relation to the other bays. There's no topology information in the model at this point, but we can do that pretty simply with just a couple of configuration options. Now we're going to come back to the sample values scheme and show that we have now added our 4th bay into the various roles. And then we're going to scroll down to the connection matrices, and we're going to see that that 4th bay got automatically connected because of the automation rules that we set up. And so that what this video illustrates is just how quick it can be to design a new substation using some of the features in these SCTs and STS in particular. Um, if you think about what it would have taken in a conventional substation design with all the drawings to add that fourth bay to the template, I mean, you're going to be copying and pasting probably some standard drawings. You got to go in and update all the names, and we're probably talking about days, if not weeks, depending on the complexity. And we just added that fourth bay into the substation in a matter of minutes. Now, there's definitely a lot of engineering work that went into creating the templates at the bay level, figuring out the data model that was discussed earlier, identifying the signals, doing the goose and sample value scheme connections, turning those into templates. There's a lot of time that goes into doing that. But once you have those libraries created, you can see how quick it is to build a substation configuration using them. The last thing that I want to touch on are some improvements that are coming in the standards. And I'm not going to get into a lot of details here, but I just want to make everybody aware of them that builds on some of these topics that we saw today. So first is 61850-9-30, which is function modeling. And this was released in December, I believe, last year. And I just took a screenshot from one of the graphics out of 90-30. It introduces topics such as function modeling, the IED specification description or ISD files, and UUIDs are some of the things that come out of that document. And these schemes that are being developed here, like this breaker failure application, these are all defined in the substation section. And one of the interesting side effects of that, or the outcomes of that, is ties in with what we talked about earlier about doing testing earlier in the project. And you can actually test the communication schemes using some of the tools that are on the market or being developed before you even pick out your IED vendor or the models, or you've allocated your functions into physical IEDs. So we can do a lot of communications verification much earlier in the project, saving time later in the project where things get more expensive. The second one I wanted to touch on, which is related to 90-30 and builds upon it, is 7-6 basic application profiles. And version 1 of this document included a document template that's used to describe your scheme. If you have, like protection criteria documents or functional specifications, there's lots of different names for them. That's what this version 1 did. Version 2, which was released in December as well, alongside 90-30, includes an XML representation of the BAP, and so that you can standardize the creation of those Bay templates and the goose and sampled value schemes that we looked at earlier in that video. And I'm positive that the various vendors are working on building out the tooling related to these two new documents. And so I think these two standard parts are going to have the capability to even further improve the efficiency and the quality of the digital substation designs that we're all looking to produce. And in summary, we talked about the Quick Connect digital substation idea. Again, moving a lot of testing up front in the project. where it's easier to make changes, less expensive to make changes. We talked about the advantages of the system configuration tool over the bottom-up approach, and then we talked about some templating ideas, the Bay templates, the Goose and sample values templates, and the automation that STS enables, and the features that they have there to really improve the efficiency of building these digital substation configurations. And I think our thought is that uh, these three topics, whether you pick all of them or you pick and choose one or more, have the ability to decrease cost of deploying new substations. I think they have the potential to decrease the schedule that it takes to deploy a new digital substation. And I think we can do that by being more efficient and really improving the quality of the configurations that go out. And with that, I think I'm done, and I'm open to questions.
Okay, thank you, Keith, for a very interesting talk. Are there any questions? No, or online? Maybe you can tell me if there's one. I have a couple of questions, Keith. So you, in the beginning of your talk, you talked about this modular approach to the actual physical substation. So you want to build the building in a factory, ship it on site, have it already tested, and then the same to PIUs, and then you just need to do an end-to-end test. That seems to me kind of the same approach that you would have in 650 top-down engineering, right? You have basically templates that you can rely on that are well tested, and you reuse the engineering decisions. Is this something that you see as a trend? Do you know if anyone is doing that, and is doing that maybe in conjunction with top-down engineering and the templates that you mentioned?
I know of one utility in the U.S. here who is doing the quick connect substations for the physical control building, and the merging unit cabinets. We worked with them on the engineering of their pilot of this concept, which went into their training center. We and the video that I showed, that substation there is what we built for them in STS. So we did use the top-down approach. Well, it was kind of, I guess it wasn't strictly top-down, because we knew the vendor and the hardware that was going in there from the very beginning. But we did try to apply many of the top-down ideas in the design. We did make use of those Bay templates and the Goose and sample values templates with the automation there for that project. We handed that over to them, and I don't know if they have determined what their engineering process is going to be at this point. I think they're still learning about that and evaluating different things. But when we did the configuration for that project, we did use the concepts that I presented today.
Okay, and that kind of leads me into another question. So we've been talking about this here as well, that there's a bit of a difference in terms of 6150 adoption and acceptance between Europe and the US. And the impression that many people have is that the US is a little bit more inert, and they're not adopting this quickly. But you also mentioned there's lots of work to be done, and I assume that in the US you have a similar problem as in Europe, that it's really hard to find people who know how to do the work, and you have to train them up, and it's all a very time-consuming process. And given the inefficiency of this classical top-down approach, where you saw that on the slide, you have 4 ICTs, you have to do 12 exchanges or something ridiculous like that. This seems to me kind of like that would build pressure towards 61850 adoption and going towards a top-down engineering approach. So why do you think the US is kind of not adopting as quickly and is more skeptical of top-down engineering or of the 6150 engineering process?
I don't know if I can give the reasons why we're a little bit further behind, but maybe I can say that over the last year and a half, 2 years, we have noticed a big uptick in the number of utilities that are um, everything from interested to 61850. They're starting to talk about it. They're starting to reach out to different industry groups, all the way to utilities who are deploying fully digital substations. I know that there's one utility in the Northeast that has recently commissioned their first fully digital, process bus, station bus, um, digital substation. And then there's many utilities that are kind of in that spectrum in between just starting to think about it and actually deploying it. um, there's utilities that are deploying their pilot substations at this point. There's lots of utilities that are playing with it in the lab. And so I guess I can just say that I think we are seeing the attitudes change in the US. And I think what you touched on there with um, the amount of resources, engineering resources that are available are maybe not enough to meet the demand if we have to build all of these substations that we're being asked to build in a conventional way. So I think that's part of what's driving this uptick that we're seeing in the U.S.
Okay, thank you. And any questions in the meantime? Yeah,
Keith, you mentioned about building the libraries and then using automation for rolling out to the substation.
Mhm.
Just to give the timeline, how long did it take for you, or how much effort was it for you to build the libraries, and what was the return for you in terms of automation?
That's a good question. I wish I would have kept better records of how long it took us. But as I mentioned before, we went through this a few times, and because the design was evolving as we were doing the engineering, and so it wasn't like we just started at the beginning and went until we finished. There was a significant investment in the libraries and getting those right. We did create like the Goose libraries and the sample values libraries, and then we would realize that maybe we messed up, so we would have to revert those back to a non-templated instance of those, and then we would go through the templating process again after we made our change. Really, the reason that we one of the main reasons that we chose to do this with this project is we knew that things were going to evolve throughout the project, and using a tool like STS allowed us to quickly adapt to those changes, bring in those updated ICD files as they evolved, and map them onto the specification that we had been building. If we had done this in a more conventional way, depending on the tooling that's available with the different vendors, and I know this is all evolving as well, but that can take, if you change the ICD file, sometimes you have to delete the device completely and then remap everything, and so we really wanted to take advantage of the having the data model and the specifications separate from the actual physical implementation.
Thank you, Keith. There's also a question online. So, your example showed making a new instance of a Bay template in minutes. What additional effort is still required for vendor-specific settings? Do these need to be managed outside of the template process? That's the first part of the question. So,
Yeah. For vendor specific. Now, when you say settings, could you clarify by what you mean by settings? Protection element settings. Yeah. So we didn't model the settings in our configuration. The 6150 does have the ability to model some protection settings. We didn't do that. So yes, all of the protection element settings, pickups, time dials, curves, all of that type of stuff, that was done by the protection engineers outside of the scope of IC 61850 configuration.
and the next part of the question is, do you see this effort being reduced moving forward with the developments in 90-30? or other areas of 6180?
Yeah, I do. As I mentioned towards the end of the presentation, I think both 90-30 and 7-6 have a huge potential for making us even more efficient and providing better quality configurations. And one thing that I didn't mention in the presentation, another one that I'm really excited to see coming along is 6-3, which is the OCL object constraint language, which allows us to perform further validation on the various SCL files, both standard validation as well as utilities, integrators, end users can create their own rules to validate the SCL files. And so, yeah, I think the combination of 90-30, 7.6, and 6.3 are really gonna to give us a big leap forward in making these configurations more efficient.
Thank you.
Okay, does anyone else here have a question? Because if not, I have some questions. So Keith, you mentioned, you said something about you'll be able to take your specification and then already test that without having made any decisions yet regarding the devices. And so I wonder if in 90-30 there's this new element called behavior description that allows you to also not just specify logical nodes and the signal exchange between logical nodes, but also logical behavior. As in, how does a logical node actually behave when it gets a certain input and output? And I wonder, this is something that could be simulated. Is this something that you think will catch on? Do you see a use there from a utilities point of view to go for all that effort to specify the behavior? Or do you think this is not something that people will adopt?
That's a great question. I do see the potential there, but it's hard. I'm not very good at predicting the future, so I'm not sure. Maybe some of your utility customers there in the room would be better suited to answering that question about whether or not they'll adopt it. But personally, I see the benefit of it. But adoption, I think, is another question.
Maybe this is also a question for Jackson, because I think you at least DTM can do that, if I'm correct. So is that something that you already see where people are interested in to like define their own behavior, or are they happy to use, let's say, a default behavior that someone else might provide for them?
So Elia, a utility in Belgium, has, in my opinion, kind of led part of that effort in designing with Keith and other folks 90-30 and 7-6. An proof of concept project was done that you guys might have seen a presentation on at this conference last year. Yes, that is something that people are interested in doing, particularly Elia, and people like that. So the goal being you can specify exactly what you would like your IED to be capable of doing. How do you want protection and control functionality to be implemented? And from what I understand, you can provide that as a specification to vendors, and then they are responsible for coming back and saying whether or not their devices are capable of meeting that specification. I haven't seen it take off. We don't have people lining up at the door asking for it, but as Keith mentioned, I definitely see the benefit there, and it's something that I expect to see more interest in coming forward.
Yeah, Ebert?
Is this only for the tendering phase or also for the engineering phase?
From our perspective as a testing and simulation tool, we can take that behavior that might be specified. I believe according to the standard, it could be specified on paper, just written out, or it could be in 61.131. So from that standpoint, we can simulate the functionality of that device within the testing tool. In terms of actually taking that 61.131 and implementing it on the device, you'd have to talk to the device vendors. I would be pleasantly surprised if that's implemented. I think it's more of a documentation of the functionality that you would like than it is actual configuration that would be pushed onto the device.
Okay, any other questions or comments? Yeah.
Keith, you showed us a nice graphic of documentation feature from the IED, the inputs and the outputs. Is it coming from Helinks, or did you build something by yourself, or has Andreas plans to do such a nice documentation tooling.
Yeah, I'll bring that slide back up here real quick, and then explain. Yeah, so this is a tool that we built. We don't sell it. We're not really a software company. We've worked out an agreement with a utility here to provide these diagrams kind of as a service on an as needed basis. But yeah, this diagram is generated by a tool that we created, and just to reiterate, like I wasn't trying to sell the tool or anything. I'm just trying to point out like the power that's in the SCD file, and that diagrams like this and other documentation can be generated automatically from the information that's already in your SCD file without having to, take that information and draw it all by hand.
And maybe to add to that, as Helinks, we are thinking about stuff like that. One thing that you can do already, if you have some programming knowledge or scripting knowledge, you can do something like this and then hook it into Helinks as a launch configuration. And so that way you could have output an SCD file, click a button, and then it would generate a series of diagrams, whatever you're doing with the SCD file. So that would require your own programming, but again, it's something I might touch on later in the wrap up that we are thinking into that direction as well. Okay, I have one last question / comment, Keith. So you did mention 6-3 OCL. I personally think that this is a really cool development, and I'm wondering, could you tell a little bit to the utilities in the room or all the users in the room if they're interested in that, how to get started and why they might want to use something like that? Yeah, could you just talk a little bit about that?
Yeah, so starting kind of from the basics, so IC 61850-6-3 describes the use of object constraint language, or OCL, for validating SCL files. And the reason that we need something like this is that, yes, the SCL files are validated against an XSD schema, but that schema isn't powerful enough to enforce all of the rules defined in the Part 6 standard and throughout other standard documents in 61850. So OCL adds a layer to that validation that is infinitely more powerful than the XSD schema. And the task force working on 6-3 has written the document, the Part 6-3 document, and is also working on developing rules that will be made available through the IEC website that implement the requirements of the standards that XSD itself can't implement. And if anybody's interested, I can give some ideas here in a minute. But there is an open source tool called Rise Clips that allows you to execute these rules against one or more SCL files. And I know that there's also some vendors, I think Jackson, developing their own software tools that make use of Rise Clips to execute these SCL rules against your SCL, the OCL rules against your SCL files. And not only can there be rules for released by the standards group, by working group 10, which check requirements of the standard, but individual utilities can also write their own rules to validate their specific implementations. And so if you have some standard rules that you want to make sure get implemented at each station, you can build those as OCL rules and run them against your SCL files. And one of the reasons I'm so excited about this is that in the IOP the last couple of times, one of the largest areas that we still see issues with interoperability is with the SCL files, and things like OCL have the potential to greatly improve that interoperability between the various tools and the various vendors. If you want more information, I'm happy to share it. We can go through a tutorial and things like that at some point, but that's the basic introduction to OCL, I think.
Okay, thank you, Keith. Yeah, I think this is worth checking out. Rice Clips, they have like a whole tutorial on how to set up that environment, and you can start writing your own rules. And you can start simple by just saying the IEDs need to be named in a certain scheme, and you can make really complex stuff. Very cool. Okay, thank you so much, Keith. You also get the obligatory cheese slicer. I'm going to hold it to the camera so you can see what you're going to get.
Oh, very nice.
I'll hand this to you. I'll see you at some IEC meeting probably, and then you'll get it. There's also a cutting board with your name on it. So yeah, pretty.
Thank you very
fancy.
much.
Yeah. So that's kudos to SPI. They organized that all. Okay, thank you. And now I think we are ready for the next speaker. So